Hello and welcome to this presentation, a verified decision procedure for the first-order theory of rewriting for linear variable separated rewrite systems. This is work done by Alexander Lochmann, Aart Middeldorp, Bertram Felgenhauer, and me, Fabian Mitterwallner. After a short introduction, I will describe what the first-order theory of rewriting is and dive more into the theory behind it, more specifically on trig automata and the decision procedure itself. I will then present some new concepts or extended concepts, such as multi-hole contexts and anchored ground tree transducers. After which I will talk about a few details of the formalization and then conclude. When researching rewrite systems, it's natural to talk about properties of such rewrite systems. Here you can see three of them: ground confluence, normalization, and consistency. At the left here presented as first order formulas. There are many tools to talk about specific properties such as ground confluence, confluence, or normalization. However, it would be nice to have a tool which works in the full first order theory of rewriting as presented by these formulas on the left here. There are some results to this extent. The first one here is a theorem by Touchet and Tisson, which states that the first order theory of rewriting is decidable for ground TRSs. This limitation to ground is of course necessary for it to not be Turing complete and therefore decidable. This can be generalized a little bit more, first to left linear right ground term rewrite systems, which has been done in the past. And here we will generalize that a little bit more. There is, however, a limit to how far we can generalize this, of course. And here's a result by Treinen, which states that first order theory of one-step rewriting is undecidable for linear TRSs. And this is already very limiting, since one-step rewriting means that we only have a single predicate in the logic, which is the single-step rewriting. And already for linear TRSs, this is undecidable. So there's not much room to generalize more. Based on the decision procedure by Touchet and Tisson, the tool was written for it. This was done by Franziska Rapp, working together with Aart Middeldorp. And this tool takes as input a property in the first order theory of rewriting, which is a formula as seen before. And it also takes a left linear right ground term rewrite system as input. The tool then determines an answer, either yes or no, corresponding to if the property holds on the given TRS or not. Of course, the tool may also run out of time or out of resources, hence it can also time out. This restriction to left linear right ground systems, as mentioned before, can be generalized a little bit. And we generalize this to linear variable separated TRSs, which is implemented in a newer tool, FortH. Variable separated TRSs are different than normal TRSs. We drop the usual constraints. However, we require variables on the left-hand sides of rules to be different than the variables on the right-hand sides of rules, so they don't share any variables. And linearity is still also important. The decision procedure of both the Fort and FortH, and as described earlier, is based on trig automata techniques, and we will get into that further a little later. Of course, when using these tools, the question arises how correct these results are that we get. And to ensure correctness, we came up with the following idea, or this is our approach to this. First, we want to formalize the underlying decision procedure in Isabelle Hall, our proof assistant. Then make the formalization executable to generate a certificate checker, which can then certify the answers by the tool, given that, that the tool outputs a certificate language, which also has to be developed. In this presentation, we will talk about the first step in this process, formalizing the underlying decision procedure. The results have already been reported in CPP 2019 and 2020, so this has been a while in the making. But what is the first-order theory of rewriting? It is a first-order logic over the language L without any function symbols, but it contains the following binary predicate symbols here. Models for the language L are finite linear variable separated term right systems. However, we restrict the signature such that the set of ground terms is non-empty. This is equivalent to requiring at least one constant to be in the signature. This is needed because the set of ground terms here serves as the domain for the variables in our formula over L. The binary predicates mentioned are binary relations over ground terms and have the obvious meaning, such as the arrow is the one-step rewrite relation. With the star, it is the reachability relation or the transitive reflexive closure of the rewrite relation. Equality also means the obvious thing. Naturally, we want to talk about other properties and predicates of rewrite systems as well, such as conversion and parallel rewriting. And there's many more, of course. As I mentioned, the procedure is based on tree automata techniques, and we use bottom-up tree automata, which are defined, as you can see here, over a signature, a set of states, a set of final states, and a set of transition rules. Transition rules come in two different shapes. On the left here, you can see the normal transition rules where we have a function over n states, which map to a state on the right-hand side. Or the second kind of transition rule is called an epsilon transition, where we have a single state on the left and a single state on the right. The set of ground terms accepted by a tree automaton is we call the language of the automaton, and it is the set of ground terms which can be rewritten to a final state using the transition rules of the automaton. Any set of ground terms which is accepted by such a tree automaton is called regular, very similar to normal finite automata. Important theorems for later and for the procedure is that regular languages are closed under Boolean operations, such as intersection and union and so on. And checking emptiness of a regular language is effectively decidable and is also used in the procedure. Now, since tree automata only accept ground terms and we want to represent binary relations or even relations of higher arity, we need to somehow encode multiple terms as a single one. This is done by extending the signature, as you can see here, by a fresh constant bottom. And then as the new function symbols, we use strings of the previous function symbols and bottom. The arity of these new function symbols then is just the maximum of the arities of the function symbols it contains. And this is how we encode these n-ary relations. So an n-ary relation contains the terms T1 through Tn if the encoding of the terms T1 through Tn are in the relation. Details of this encoding are not important for this talk, but they can be found in the paper, of course. N-ary regular relation then is just the relation which accepts the encoding of n terms. And if that set is regular, then we talk of a regular relation, an n-ary regular relation. And the specific case that we use mainly are binary relations, and we call them RR2 relations, or in general, we will talk of RRN relations for n-ary relations. So how does the decision procedure work? Here's an example. We have this formula here, which represents normalization of a TRS, and we want to figure out if this holds for a given TRS. To do this, we construct automata which accept ground states from the bottom up, starting with the atomic subformulas. Here they are S reaches T and T rewrites to U. So both of these are RR2 relations, and therefore regular languages, and we can construct these automata. To then construct larger parts of the formula, we use closure properties on these automata to move upwards in the formula. Here we start off with the right subformula represented by the automaton A2. And since we first have this existential operator for exists U, we have to project away this U, which is done by this pi1, which projects to the first argument of the binary relation. This then is the set of all ground terms which can be rewritten in a single step. Since we have the negation in front of this formula, we also take the complement of the automaton, as you can see here, to construct the automaton A3. And this is then the set which accepts all ground normal forms. To then combine this with the automaton A1, we first have to make sure that the arities match, since we have a unary relation in A3. We first have to cylindrify this. This is simply done by constructing the product with the set of all ground terms on the left here. Using this, we can then construct the intersection with the A1 automaton. Since outside of this, we again have the existential over T. We again project to the first argument, which then represents the set of all possible S's of the formula. Since this is universally quantified, this should accept all ground terms if the formula holds. And this can be easily checked using emptiness by checking if the complement of this automaton is empty. If it is, then the formula holds. So in other words, the decision procedure boils down to constructing these RR2 and RN relations in general in a bottom-up way, and then combining these using closure operations. And on the outermost automaton, we check emptiness to determine if the formula holds or not. So the state-of-the-art procedure uses ad hoc constructions for the automata representing all these binary predicate symbols. And here are just a few examples. There's many of them, of course. And there's individual methods for every one to construct the automaton, with the exception of a few, which can be obtained via closure operations of other relations. The goal for the formalization was to reduce the number of these concrete constructions required and construct more of these predicates via the closure operations on predicates. Why do we want this? Well, the advantage is that it comes with a greatly reduced formalization effort. If we would not do this, we would require correctness proofs for every single construction mentioned above, which, as you have seen, can be quite a few. And if we use more closure operations, we need only a correctness proof per operation. This also results in an independent and more expressive tree automata library, since these closure operations don't necessarily have to be related to the first order theory of rewriting. They extend to normal tree automata as well. And this is the result. What you can see here is a formal grammar which represents the first order theory of rewriting as we construct it. And here you can see that we only have a single primitive for the binary relations, which is this root step relation here. And it presents the root step relation, as I said, for linear variable separated TRSs. All other relations are then obtained by closure operations on this. The A stands for anchored TTT relations. What this exactly means, we'll see later. In addition to these, we also have the R2 relations and its closure operations. And we have just normal tree languages, tree automata for unary predicates. Using all these closure operations, we can then construct and represent all the other predicates that we need for the logic. We won't go through all the closure operations you can see here, but as seen in red, this is important. This is the multi-hole context closure, and we will see what this means in a moment. So what are multi-hole contexts? A multi-hole context is just a term where we add this special constant to the signature. We call it a hole. It's this box symbol. The set of all multi-hole contexts is denoted by C, and we can apply a context, multi-hole context with n holes to the terms T1 through Tn by just replacing the holes from left to right by the terms T1 through Tn. In general, we can also apply this to n-ary relations or binary relations by just replacing all the terms in our relation, applying the context to the terms in the relation. For the procedure, we sometimes further restrict the multi-hole contexts we use. We do this in two ways. First, by the number of holes. So in the superscript here, you can see this one. This denotes that we look at multi-hole contexts with exactly one hole. If we use the greater than symbol, that means the context contains at least one hole. And the greater than equal symbol means that we have no restrictions and we can have an arbitrary number of holes in the context. The second restriction we use is on the position of holes. This is denoted in the subscript. If there is a greater than symbol, this denotes that we look at multi-hole contexts where every hole occurs below the root position. The epsilon denotes that every hole occurs at the root position, therefore there is only one hole. And again, the greater equal means we have no restriction on the position of holes. We use these in combination, of course, so we have the multi-set, the multi-hole context closure for relations NP, where n is the restriction on the number of holes and p the restriction on the position. So if we look at an example here for the root step relation, we get 8 different relations. It's not 9, and we'll see that in a moment. The most obvious one, if we restrict to the root position and have at most one or exactly one hole, then this just stays the root step relation. If we then allow multiple holes or have no restriction on the number of holes, this means we can also have a context without any holes, which means we have the reflexive closure of this root step relation. And if we restrict such that we have at least one hole, well, since we also restrict the position to the root, this means we have exactly one hole, and it's just the root step relation. Now looking at the positional constraint, if we have no constraint on the position, but restrict to a single step, we get the normal rewrite relation, single step rewrite relation. If we allow an arbitrary amount of holes, we get parallel rewriting. And if we restrict to at least one hole, then we get this parallel step relation where it's non-empty, meaning that the standard reflexivity is missing. Now, if we restrict to positions below the root, we can describe rewriting below the root, obviously. If we here allow arbitrary numbers, we get parallel rewriting below the root. And if we restrict both the position and the number to be greater, then we get parallel rewriting below the root, which does not allow the empty step. And this non-empty rewriting is denoted by the dot above with arrows. Now, the nice thing about these closure operations is that they are regularity preserving. In our case, we apply this to R2 relations. So multi-hole context closure of an RR2 relation remains a RR2 relation. However, this extends to arbitrary tree automata and hence can be used in other settings as well. All right, on to another new concept used by us, which is anchored ground tree transducers. So let's first talk about what are ground tree transducers. They are constructed of two tree automata, A and B here. We speak of the set of states of a GTT, which is just the union of the sets of the automaton A and the automaton B. And these GTTs accept binary relations. So the language of this GTT is the pair of terms S and T, such that S reaches a mixed term U. A mixed term here is a term which contains both function symbols and states. So if S reaches U by rewriting with the transitions of the automaton A, and T reaches U by rewriting with the transitions in B, then the pair ST is accepted by this GTT relation. Now, what is a anchored GTT relation then? Well, this is just a different, we use a different acceptance criterion here. We also speak of the anchored language of a GTT, and that is, we accept pairs of terms that rewrite to a state and not a mixed term, meaning S has to rewrite to Q using the transition of A and T using the transition of B to Q, and where Q is a state and not a mixed term. The reason we use anchored GTT relations, firstly, is that the root step relation is such an anchored GTT relation for linear variable separated TRSs. All anchored GTT relations are regular, meaning these relations can be constructed as normal tree automata, and this is also what we do in the procedure. Here you can see the relation between the anchored language of a GTT and the language of a GTT. Obviously, the anchored language is a subset of the language, and interestingly, the multi-hole context closure of the anchored language is the language of the GTT. Another reason why these GTT relations are interesting is they come with nice closure properties. For example, GTT relations are closed under composition, transitivity, and inverse, whereas, for example, our two relations are not closed under transitivity. This is why we require them. However, the anchored GTT relations that we introduce have even better closure properties. Here, in addition, they have union, complement, and intersection. We also use two modified versions of composition and transitivity for anchored GTTs. The details are not so important here and can be read up in the paper, but essentially these commutation and transitivity operations involve context closures as well, but this is not so important for the moment. So how do we represent other predicates using this? This is just an example where we, you can see at the bottom here, we use as a primitive our root step relation. And first we combine the inverse of the root step relation with the normal forward step, which gives us a single conversion step at the root. If you know term writing, this is quite obvious. Now you can see this special transitivity operation, and on the outside it's the multi-hole context closure. Interestingly, these commute in a nice way, where we can switch the operations such that we have the multi-hole context closure on the inside, and the transitivity or the transitive closure turns into normal transitivity, and not this het version that we present. If we look at this relation in the inside, where we have the multi-hole context closure, we can see that we no longer restrict the position because of the multi-hole context closure. And this also involves the empty step or the reflexive closure. Therefore, this is equivalent to just conversion here. And this is how we also represent conversion in the decision procedure. So as you can see, we can represent all we need or predicates that we need for the decision procedure in this way. And we only have to formalize the closure properties and get many more predicates for this. So a few words to formalization itself. As mentioned earlier, this builds on previously presented results. And here in brackets with the plus, you can see how many lines the formalization had before these new results, meaning this was presented previously in CPP and TACAS, while before the brackets, you can see how many lines we've added during this work. So in total, we've added 5,030 or 29 lines to the formalization, which already had 9,447 lines. Of course, the work done previously also had to be adapted slightly and modified and improved. So this line count is not doesn't give the full picture. The full formalization can be found at this link. This contains the theory files, but also a HTML rendering of the theory files, which are nicer to read. So concluding our contributions, we have written the first complete formalization of the decision procedure of Fort. And we also prove correctness for all the representations of the rewrite relations we use by showing that they are equivalent to the rewrite relations from ISA4, which is the Isabelle formalization of rewriting. As mentioned in the introductions, the next steps would be to make the formalization executable and generate a certificate checker, as well as design a certificate language. Both of these things have happened in the meantime and will be presented in the upcoming TACAS. Future work regarding this formalization has many possibilities, of course, but one that might be interesting is that the current decision procedure is limited to ground properties, so we can only describe rewriting over ground terms. However, there are techniques for certain properties to extend this to general rewriting. This uses signature extensions and could also be formalized, of course. This is the end of the presentation. Thank you very much for watching this video. Thank you.